Okay, so welcome to Math 150, Section 1, 2021. What is it, maybe lecture 16? And so what I want to do today is I want to talk a little bit about integration. And so if there are specific questions you have, some of you have been emailing me, which is great, and I will incorporate those into the lecture. So if there are things you want to see, you have to let me know. So the biggest problem in a lot of these classes, in these lectures in Math 150, multivariable calculus, is not multivariable calculus. It's either doing algebra or doing one-dimensional calculus. The amount of multivariable calculus you do in a lot of these problems is very minimal. When we did Lagrange multipliers, it was to set up the gradient of f is equal to lambda gradient of g, and then you had a g constraint as well, and then the rest was just algebra. For multivariable calculus, there's really two places where the multivariable occurs. Sometimes in a change of variables, and sometimes in switching the orders of integration. Those are the two major techniques. In Calc 1, we have a lot of techniques of integration. We have integration by parts, we have partial fractions, we have U substitution, we have trig substitution. You need to know these. I am not going to give you partial fraction questions. You should know how to do that technique. I'm not going to really focus on that. If we do trig, it's not going to be that much trig substitution. What I really do is U substitution and integration by parts. Those ones we will use again and again. So if you're not comfortable with those, please talk to the TAs, talk to me. So the big content in this lecture today was horizontally simple, vertically simple regions, and trying to write down the bounds of integration. If you could choose a shape to integrate over in the plane, what shape would you choose? Rectangle. So for this class, a rectangle is better than a circle. So why does a rectangle beat a circle? So the reason a rectangle beats a circle is the bounds of integration don't depend on each other. X goes from A to B, Y goes from C to D. It doesn't matter. One variable doesn't change the other. If I give you a circle, and I want to integrate this. You want to integrate first with respect to X or first with respect to Y. It doesn't matter. First loud voice wins. Y. And I'm assuming that that's not a question. That is. So we integrate first with respect to Y. So what I'm going to do is I fix an X, and then I determine the range of Y. So X is fixed, and then Y, if this is x squared plus y squared equals 1, we have y goes from negative square root of 1 minus x squared to the square root of 1 plus x squared. And then x goes from minus 1 to 1. So if I wanted to set up the integration, it would be x goes from minus 1 to 1, integral y goes from minus square root of 1 minus x squared to the square root of 1 minus x squared, f of x comma y, dy dx. Why did I write dy first and dx second? I'm integrating with respect to y first. Do I need to put a y subscript down here? No, because I put the dy over here, it has to be the y variable that's being integrated on over here. Is it bad to put the y? Absolutely not. The more notation I put down, the easier it is to just glance and look at what's going on. For those of you who think I have not used enough chalk on this problem, I could even put a bracket like this to just really emphasize I'm doing this integration first, and when I integrate this, I get a function of x. So I'm integrating out the y variable. And then I integrate with respect to x. And note at the end of the day, I'm going to get just a number. Now the bounds of integration depend on x. So depending on the value of x, the range of y is going to be different. This is one of the reasons why polar coordinates are awesome. If we shift to polar, x squared plus y squared equals 1 becomes r equals 1. And then the circle x squared plus y squared is less than or equal to 1 just becomes the rectangle r less than or equal to 1. And so in polar coordinates, if I do theta here and r here, this would be 1, this would be 2 pi, and I would just have a rectangle. And now what I can do, theta goes from 0 to 2 pi, r goes from 0 to 1. So it'll be f of r cosine theta, r sine theta. And now this is where things get a little interesting. It's not just dr d theta. And so we'll talk later as to exactly what goes in there and why. For now, I'm going to just state it's r dr d theta. This is how the area element dx dy transforms. So I have a little infinitesimal blurb over here, and that's going to become something over here. And I need to know, how does that dx dy transform? Think of it as the exchange rate, converting from dollars to euros. And so another way to look at it is, if I assign units, x and y are in meters, this is in meters squared, this is an area. Angles are unitless. So dr d theta is just going to be in units of meters. I could really view this as dr times r d theta, because r d theta is going to be a length. We'll talk more about this when we get to the change of variables. What's nice now is if this function splits into, say, some function of r and some function of theta. Let's assume that happens. It's not always going to, but it often will. If that's the case, then this is the same as I can integrate theta goes from 0 to 2 pi b of theta d theta, integral r goes from 0 to 1, a of r dr. And again, the reason is, if this function f of x, y depended on just x and y, could I split things up? Could I just pull outside the x dependence? I could pull outside the x dependence, but I'm going to be a little bit careful when I integrate the y. I am still going to get some x dependence. It's very nice when I have a rectangle, and this bound to r is independent of theta. It basically says I can treat this as two one-dimensional problems. I can just do the calc 1 integral for r, I can do the calc 1 integral for theta. The multivariable calculus is this transformation. So rectangles are the nicest regions to work on. This is why we love cylindrical and polar and spherical coordinates, is they take shapes that are not rectangles or boxes, and they give us a coordinate system where they are boxes. And that's going to make the integration a lot easier. So the general case is, what if I give you a donut? So is a donut a horizontally simple region? Can somebody tell me what a horizontally simple region is? Good. So a horizontally simple region is you enter the region, you stay in, and then you leave it. You never enter, leave, enter, leave. So if you look at the circle and the rectangle, these are horizontally simple. Once you enter, you stay in it for a while, and then you leave, and then you're gone for good. Is the donut horizontally simple? Is it vertically simple? Damn. Right? So if we have methods to integrate horizontally simple regions, we're stuck. There are some tricks you can do to deal with the donut. Anybody know a trick that you could do to kind of convert this to horizontally simple? Okay, so how would you do two circles? And what do I do to the two of them? I could subtract. So I could treat it as two problems, right? Is it better to treat it as two problems? Yes, if I have a technique that allows me to handle horizontally simple regions. I would much rather do two problems like that than try to do one harder problem. Where now for this one, I have to figure out, if I fix x over here, y goes like that, but over here, dear Lord, right? I don't want to do that. One possibility you could potentially do is you could try to break this up into maybe quarters. And then each one of these would be horizontally simple. And you would have 4 such integrals to do. Or you could maybe do it as a semicircle. I think it's much easier to just break it up as to the big circle minus the small circle. And so always be thinking, how can I take whatever I'm given and reduce it to what I can do well? So this is the principle of the hammer. If all you have is a hammer, pretty soon every problem looks like a nail. If you are good at something, convert it to what you are good at. And then just hammer away, use your techniques. Okay? So what we want to do is we want to figure out how do we find the upper and the lower bounds of integration. And this is going to, for the most part, be algebra. This is where people have the greatest difficulty. It's not in the actual integration, it's in setting up the bounds to integrate properly. This means you have to be able to graph decently. On a homework problem, what can you use to help you graph? Mathematica, any kind of graphing program, absolutely use it to plot things and get a sense of what they look like. On an exam, do you think I'm going to give you a tremendously horrible region to plot? If you are plotting it and it becomes tremendously horrible, what does this mean? You're doing something wrong, or I'm a lying sick bastard. Those are the two options, right? If I'm a lying sick bastard, you're screwed, there's nothing you can do. So as an operating assumption, assume that you have probably done something wrong if the bounds of integration are terrible. And it's an exam problem. On an exam problem, I'm not going to give you something that takes 2 hours with horrible bounds. So here's a very popular theory. Let's let y equal x squared and y equal x square root of x. So let's plot this. What does the first one look like? Y equals x squared. What is that? It's a parabola. And we'll assume 0 less than equal to x less than equal to 1. You can probably see the punchline coming. So I can actually draw parabolas. So here is y equals x squared. And here's the point 1, 1. What about y equals square root of x? What kind of curve is that? Okay, what kind of curve? What is the name of that curve? You all know the name of this curve. I know everybody in this classroom knows the name of the curve y equals square root of x. I feel like a magician. By writing things in a certain way, I can confuse you. 2 of my friends took a year off college to help the amazing James Randi set up his institute to debunk psychics. Yes. It's not an exponential. Exponential would be e to the. It's a parabola. Y equals the square root of x. This is the same as y squared equals x. It's a parabola. I've just switched the roles of x and y. But by switching the roles of x and y, I can hide it, I can disguise it. It's just a parabola. Instead of a parabola pointing up, it's a parabola going to the right. And so here, is y equals the square root of x, which is also going to be at the point 1, 1. So what I want to do now is just very slowly, very carefully set up how I would do an integration over this region. So I want to integrate over this region. I have two choices. I can integrate vertically, or I can integrate horizontally. We're going to do it both ways. Which way do you think is easier? Integrating first with respect to x and then y, or first with respect to y and then x? So I want to fix x and then look at how y ranges, or fix y and look at how x ranges. Fix x, because if I fix x, I go from x squared to square root of x. Things are already set up nicely for me. So in this case, this is going to be my lower curve, my bottom. This is going to be my upper curve or my top. I need notation. I can use F1 and F2. I can use FT for top and FB for bottom. I can use T for top and B for bottom. There's lots of different ways. I can use U for upper and L for lower. There's lots of different notations you can use. Does anybody have a strong preference? If not, I probably will do maybe 1 and 2. I'm happy to do upper and lower. Let's do upper and lower. So let's have this one be L, and now this one is going to be U. And now we have to think, is it a function of x or a function of y? Well, we're fixing x, and then we're marching up. So if we're fixing x and we're marching up, we want y as a function of x to get where do we start and where do we end. So we would want this to be y is equal to L of x, and here we want y is equal to U of x. So fix x, x goes from 0 to 1, and then y goes from L of x, and what is the curve L of x? This particular, it's just x squared, to upper of x, and what's upper of x? Square root of x. And so we get the integral, x goes from 0 to 1, integral, y goes from x squared to square root of x, f of xy dy dx. Does this bother you that x squared comes first, but x squared is less than square root of x? Shouldn't x squared be the higher value? 2 squared is 4, 4 is larger. So why is this not wrong? Because it's from 0 to 1. So if you're ever not sure, take a number and test it. Let's take x to be 1/4. If x is 1/4, then x squared is 1/16, and square root of x is going to be 1/2. Oh, good. I do have things going in the right direction. So when you're ever unsure, just take some specific values and test. If your upper value is below your lower value, you probably made a mistake. Any questions on how we set this one up? So now we have to do it the other way. So now we have to do the inverse functions. I've chosen nice examples here to calculate the inverse functions. How many of you remember finding inverse functions in high school? So I'm doing algebra 2 with my son right now, and I don't like the way the book is doing inverse functions, so this is my chance to get it out of my system. So let's do inverse functions. Let's say y equals x squared. So I want to find what's the inverse function. So f composed with g of x equals g of f of x. This is is what it means for two functions to be inverses. And so I want to figure out what function will return me to x. What function will invert squaring? So what do you think the opposite of the squaring function is? The square root function. So let's try to think about how we want to phrase it. Here, I give you an x. So given x, we find y. To invert, given y, what was x as a function of y? That's what it means to invert. So if I have f of x equals x squared, I call that my y, f of 2 equals 4. So given 2, we output 4. So what should g of 4 be? What should the inverse be? If 2 is sent to 4, what should 4 be sent to invert? It should be sent to 2, right? So given 4, output 2. So if y equals x squared, then x equals the square root of y. And so that would be my function g of y. So I just solved for x in terms of y. I just solved for x in terms of y. Let's check. What's f of g of y? Well, what does g of y equal? G of y is square root of y. And what is f of input? F of input is input squared. So it's square root of y squared equals y. Let's check the other way. What's g of f of x? Well, f of input is input squared. So this is going to just be g of x squared. And g of input is square root of input. So this would just be the square root of x squared, which is just x. So in both cases, f of g of y returns you to y, g of f of x returns you to x. We found the inverse function. So the idea is to just do some algebra. If I tell you y as a function of x, I now want x as a function of y. Should we do another problem like this? Okay, let's do another problem. Are people comfortable with this? Can I erase this over here? So sometimes you may not always be able to invert. No. Let's consider f of x equals 3x squared minus 4 is y. So given x, this gives us a y. To invert, we want given y, what is x? What might be a problem here? So for a function, if I ask you what is the temperature now, and I tell you it's 48 degrees and 62 degrees, what should you be thinking about? I'm crazy, right? You can't have multiple temperatures. A function outputs one value, one number for a given input. Okay? The problem with the parabola is you can have multiple x's that have the same y. If I look at the plot of this, when x equals 0, it's -4. When x equals 1, it's -1. The parabola is going to look something like this. So if I give you a value of x, is there a unique value of y for each value of x? Yes. Given a value of x, there is a unique value of y. If I give you a value of y, is there a unique value of x? No. In fact, for any value of y, except y equals -4, there are two values of x that work. So I have to be careful when I'm finding the inverse. So I might want to do, say, x greater than equal to 0. I might want to put a restriction like that. And if I restrict to x greater than equal to 0, I now lose the whole left half of the parabola. And now do I have a unique inverse? Yes. So you have to be a little bit careful sometimes, but there may not be a unique inverse. So now I have 3x squared minus 4 equals y. So 3x squared equals y plus 4. So x squared equals y plus 4 over 3. So x equals the square root of y plus 4 over 3. And that will be my function g of y. So I have found my inverse function. And you can go through and you can check and see that f of g of y is y and g of f of x is x. When you look at this, is there any concern you have about this being well defined? What do we need for g of y to be well defined? Here, the square root of y plus 4 over 3. What scares us about this? Oh yeah, so when could the input be negative? Other way around. If y is greater than -4, we're okay. So we're okay if y is greater than or equal to -4. And if you look at the plot, that makes sense. As long as y is greater than greater than equal to -4, we're going to be on the parabola. If y is less than -4, then there's no x that works. And so everything is nice and consistent. And so this would be our inverse function. So it's not too bad to go through and find inverse function. Just if I give you x as a function, y as a function of x, then just solve for x in terms of y. That's all we're doing. So solve for x in terms of y. Okay. All right. Any questions about this? Okay. So now we can return to our original problem. No. We have these curves here. This is going to be y equals x squared. So how would we write this as x as a function of y? This is the same as x equals square root of y. And over here, this was y equals the square root of x. So this is x equals y squared. Now, instead of having upper and lower, I'm going to have left and right. This is going to be my left. This is going to be my right. So I would have x equals r of y, which would be the square root of y. And over here, I would have x equals L of y. Oh, so they both have a left and a lower. They both start with L. So y equals L of y would be y squared. And now I fix the value of y, and my x goes like this. So I would now, I'm integrating first with respect to x. I fixed y. So what's my range for y? Y goes from 0 to 1. And then x goes from the lower bound, which is y squared, to my upper bound, I guess I'm calling it right, which is the square root of y, f of xy, and now I'm doing the x integration first with dx dy. So I have two different ways to do the integration over this region. Any Seinfeld fans here? So I showed an episode to my kids. It was the first full episode they ever saw. It's the opposite. So one of the characters is basically the epitome of a loser. And he remarked that every decision he's made in his life is wrong. And so his friends convince him, well, if every decision you make is wrong, the opposite must be right. What is the problem with this logic? What is this implicitly assuming? There's only two options. So if there's only two options, that's correct. If there are more than two options, however, and so he starts to do the opposite of what you would expect to do in every human situation, including yelling at the boss in the job interview. And his life starts to change remarkably. If you are doing a multivariable calculus problem and you set up the bounds of integration over a region that's both horizontally and vertically simple, and the integration is a nightmare, what should you try doing? Switch the order, do the other one. So switch orders. There's only two options in two dimensions. So if one of them is not working, stop, put the paper aside, try the other one. What if the other one isn't working? Then you either have to find something new, or maybe the first one wasn't so bad after all, and then when you see how much worse the other one is. But when you have two approaches, try one for a little bit. If it's not working, try the other. This is one of the major techniques we have, is switching orders of integration. So there's a big theorem that says if your function is nice, if your region is nice, you can integrate in either order and get the same answer. It is not always the case that you can switch the orders of integration. There are functions where if you try to integrate and you switch the order, you will get a different value. Those functions all involve infinities. So it's okay if no infinities. This means your region is a finite region. It's contained in some giant circle. This means your function is well defined and it doesn't blow up. As long as stuff like that is true, you can switch the order of integration. And that's called the Houdini theorem. So this is one of our biggest techniques, that if everything is finite, you can switch the orders of integration. If things are infinite, you can still sometimes switch the orders of integration. It turns out if the integral of the absolute value in either order is finite, then so is the other, and they're equal. But for us, for everything we'll be doing, we will be having nice functions, finite regions, or the decay is so fast that we don't need to worry. So if it's not going well with one, try the other. Now this means you have to know how to do your one variable integration. And so for a lot of these integrations, one way is going to be much easier than the other. If I give you the function x e to the negative x squared y squared dx dy, which way might you want to integrate first, with respect to x or with respect to y? Y with respect to y. So if I'm integrating with respect to y, if I want to integrate e to the negative u squared, I really want a u du, right? By the chain rule, I need the derivative of the exponent. So if I give you an e to the negative x squared y squared, if I integrate this with respect to y, I need to have like a negative 2x squared y. If I integrate this with respect to x, I need a negative 2xy squared. I can multiply by negative 2y squared over 2y squared, and then this part is nice. Because now this part here, the negative 2xy squared, is the derivative of the exponent with respect to x. Right? Because if I'm taking the derivative with respect to x, y is a constant. If I didn't have the y here, I just wanted 2x. Because I have the y, I want a 2xy squared. So the hope is then, when I put in the bounds of integration, the y squared down below will go away. But I can do the x integration much nicer because I have the x there. And if I try to do the y integration first, I'm going to be stuck. So sometimes you can make life a little bit easier by looking at things and trying to figure out which way might be better. This is similar to the integration by parts. We saw that the more complicated your function is, the more choices you have for the UDV. But there's still only finitely many choices. You just go through all of them, and the hope is that eventually you will hit the one that works. All right, so this is the theory of horizontally and vertically simple regions. You need to know how to find the inverse functions. You need to carefully write down the upper and the lower bounds. If people want more practice problems, I think there's some on the web somewhere. If you can't find them, email me, and I will send them to you. They should also have write-ups as well. And just, going through with the pictures and the geometry. The more problems you do, the easier it's going to be. For some of the problems, you have interesting ways of doing things. If I give you this region over here, this triangle, if I do the triangle this way, there will be x goes from, say, 0 to 1, y goes from 0 to x. If this is the line y equals x. I could also do it this way. And if I do it this way, then it's y goes from 0 to 1, and then x goes from y to 1. So depending on how I do it, I'm going to have slightly different bounds of integration. And depending on which problem you do, sometimes one way is easier than the other. Okay? So you just have to get comfortable with trying the different options. Okay. So there was a question from a couple of people on one of the homework problems. It was the function 37. F of x, y was the sine, I think of the square root of x, y. 0 less equals x, y, less equals pi. And we wanted to integrate this. X goes from 0 to pi, y goes from 0 to pi, times square root of x, y, dy dx. And we wanted to bound it like this. And it said you use Riemann sums to prove bound points. Well, when x and y go from 0 to pi, the argument of sine is going to be at most pi. So the argument is going to be between 0 and pi. So what's the range of the sine? So in our region, 0 less equal to sine square root of pi of xy is less equal to 1. So if you look at our region, here's pi. Let's break this up into boxes. On each box, what's the lower bound for our function? 0, because we know sine is going to be at least 0. And on each box, what's the upper bound? Sorry? 1. Now, you can do better. If I take this box over here, I'm very close to an argument of pi. So I don't expect to be close to 1. But I'm just trying to get an easy balance. So we know that our function is always between 0 and 1. So in each box, the lower bound is 0, the upper bound is 1. I can just put these everywhere. And so if I can add up all the areas, what's the area going to be of the square? It's going to just be pi squared. Right? It's pi by pi. So the lower bound is going to be 0 and pi squared. And again, this is a really simple case because I have the same lower bound for each square. If I had different lower bounds for each square, I would have to take each square, multiply by the lower bound, or basically take the area of each square and multiply by its lower bound, and then sum all. But because they all have the same value, it's just going to be that value times the total area. And the upper bound is going to be 1 times pi squared. Any questions on that? Any other questions on the material? All right, so we're going to end with a nice application of the chain rule, the one-dimensional chain rule. It's to find derivatives of inverse functions. So we'll eventually use this for exponential and logarithm, but I'll do trig functions. So the chain rule and inverse functions. So what is the sign of the arc sine of x? X. The arc sine of x gives you the angle whose sine is x. So I take the sine of the angle whose sine is x. What's the sine of the angle whose sine is x? The sine of the angle whose sine is x is? Listen to the word. The sine of the angle whose sine is x is just x. I'm taking the sine of the angle whose sine is x. If I look at the triangle, here is arc sine of x. Let's call that theta. So if I make the hypotenuse 1, this angle opposite here would be x. And then this would just be square root of 1 minus x. What if I gave you the tangent of the arc tangent of x? What is the tangent of the angle whose tangent is x? It would just be x again. Listen to the rule. In that case, here's arc tangent of x is theta. So if I want an angle whose tangent is x, tangent is opposite over adjacent. Let's make this x1, 1 plus x squared. That would be my triangle. And so the tangent of the angle whose tangent is x. Let's do it the other way. What would the arc tangent of tangent of theta be? What angle corresponds to the value tangent theta? It would just be theta. Sometimes people write arc sine as sine to the -1. Sometimes they write arc tangent as tangent to the -1. A lot of people don't like that notation because it can be confused with, is it 1 over the function? These are inverse functions. I'm trying to find what function inverts sine, what function inverts tangent. And so what I want to do is I want to show how the chain rule allows you to calculate derivatives nicely. Let's say I have a of x is f of g of x equals x. We can calculate the derivative of a two different ways. Can somebody tell me what a prime of x is? So a of x, f of g of x equals x. F and g are inverse functions. If a of x equals x, what's its derivative? 1. But by the chain rule, it's f prime of g of x times g prime of x. We can solve for g prime. So g prime of x is 1 divided by f prime of g of x. So this is a beautiful relationship with f and g are inverse functions. So what it tells you is if you know one derivative, you know the other. Let's use this for tangent. So if we take f to be tangent and g to be arctangent, this tells us that arctangent prime of x is 1 over f prime, well, f is tangent, so 1 over tangent prime of arctangent of x. Does anybody remember what the derivative of tangent is? So I always have to rederive it. The tangent is sine over cosine, so tangent times the derivative of sine is cosine cosine minus sine to the cosine sine cosine squared. That's cosine squared, so the secant squared. You are correct. So the derivative of tangent is secant squared. But secant is 1 over cosine. So this is just cosine squared of arctangent of x. So we have a formula for arctangent of x, for the derivative. It's the cosine squared of arctangent of x. When you look at this function, cosine squared of arctangent of x, are you excited that this is a function you know and understand? Or does this look like a monster? So let's think about the triangle. Here's my triangle. I want to calculate what is the cosine of the arctangent of x. So if I go back to my triangle, the opposite side is x, the adjacent side is 1, the hypotenuse is the square root of 1 plus x squared. What is the cosine of arctangent of x? It's just adjacent over hypotenuse. It's just 1 over the square root of 1 plus x squared. So if we plug that in over here, this is just 1 over 1 plus x squared. That's much better than cosine squared of arctangent of x. This is the power of the inverse function. This is the power of the chain rule. What we have just found is a function whose derivative is 1 over 1 plus x squared. So another way of saying that is we've just found the integral of 1 over 1 plus x squared. What is the integral of 1 over 1 plus x squared? So if the derivative of arctangent is 1 over 1 plus x squared, what's the integral of 1 over 1 plus x squared? Arctangent. This is not a function you should have known how to find the antiderivative of. You would love to have an x in the numerator to integrate. We don't have an x, but we actually have a way to find the antiderivative. All right, so this is a good place to stop for today.